Sir, good evening, Satish sir. Sir, we'll start in 2 minutes, sir.
Satish sir, shall we start, sir?
Yes. Can you hear me?
Yes, yes, sir. Yes, sir.
Yes. Let me share.
Sir,
Let me share the screen.
sir, yes, sir. Remaining participants they will join, sir. Meanwhile,
Yeah.
so very good evening to all. Welcome to the third day of AICTE sponsored ATAL FDP and key technologies enabling 5G. So welcome to the fifth session. So now I feel very honored to introduce today's speaker, Mr. Satish Kumar. So Satish Kumar sir, who holds an MTech degree and has a strong technical background. He has been contributed to the field of wireless communication. He started his career at Urimi Systems, where he gained invaluable experience working on innovative projects. Currently, he is a senior software engineer at Mathware. It is a globally known company, and his expertise lies in software-defined radios and advanced 5G technologies, areas where he made his significant contributions. His work exemplifies the cutting-edge advancements during the future of communication technologies. We are delighted to have him here to share his expertise and inspire us with his journey. So let us welcome. So, sir, thank you, sir. Thank you for accepting our invitation. And, sir, now the session is yours, sir. You can
Yeah.
start, sir.
Thank you. Yeah. Hello all. Thanks for having me here. Yeah. Let me share the screen and we will get into the discussions. Let me know if it is visible. Hello all. So in this session, we will discuss about the what are the use cases of the 5G, why we have moved from the LTE to the 5G, what use cases are driven from going to the LTE to 5G, and what are the requirements that use cases gives us to define the 5G technology. And we will discuss about the what are the frequency ranges that is supported by 5G, and then um, we will discuss about the how the frame structure is defined for the 5G, and what are the subcarriers are spacings are supported, and then we will try to simulate a 5G waveform. We will through the MATLAB, and we will uh, I will give the info about what are the parts of that simulation. Like a simulation requires usual 5G simulation requires a if it is a downlink, it requires a PDSH and other parts of it like channel sounding. And I will give the what are the MATLAB toolbox provides in terms of the generation of a 5G signal, and what kind of documentation is available, and how to get started in the 5G work. So that information I will give along the way. So let me go to these things. So, so first we will discuss about the use cases. What are the actual use cases that will be served in the 5G, and what are the requirements that needs to be done to serve that use cases, and what are the main differences between the LTE and 5G, and what are the frequency ranges supported. So the obvious use case is that we want to have the more speed in the compared to previous technology. That is, LTE supports up to 20 megahertz. We want to go further than that. So one of the obvious use cases is the high data rates we want to support, because we are using the virtual reality and all these things. So we need to support more higher data rates in that cases. So that is one of the use case. And second is the as number of devices are very growing up, that density also increases at each base station. So we need to handle that. Means even home automation, all these things, and in each place we have more number of devices. The network needs to handle that. So the 5G should be designed in such a way that it supports the large number of connections at one point of time. And another is the uh, ultra reliable low latency communications. Um, let us take vehicle to vehicle communications and autopilot in the automobile industry. And in the medical devices also, we are using the 5G communications, where the communication is should be very reliable and should be very swift. Low latency should be present. So in that case also, to support that use cases, we are actually how the 5G physical layer also has to be designed in such a way that it supports ultra reliable low latency communication and a higher network, large number of connections, and a higher data rate. So as we discussed, um, we need to support this EMBB and URLLC previously discussed, and we need to have the low latency. LTE actually supports up to 10 milliseconds of latency. Latency means how fast the signal arrives at the receiver side. So this needs to be decreased furthermore if you want to support the higher low latency networks. So and the large number of devices should be connected, and need to increase the bandwidth efficiency, and you need to support the higher bandwidths also. And these devices also should the new technology also shouldn't consume more power also. So if you increase the bandwidth, there is a easier chance to the receiver side to consume more battery power. As we want to support the IoT devices and mobile devices, the battery power consumption is very critical. So your physical layer also should be in such a way that it shouldn't be a power hungry. And you need to increase you need to the your 5G network should be scalable and customizable to the networks also. So these requirements drives us to have the design of the physical layer also of the 5G. So we will take a look into that. So while there are many commonalities between the LTE technology and 5G technology, there are differences also in the physical layer. In the in terms of the band also, in the LTE supports up to 6 gigahertz, whereas to support higher bandwidth, 5G is designed such a way that it supports a millimeter waves up to 60 gigahertz. And bandwidth also, for LTE it is 20 megahertz, whereas 5G we will support up to 100 megahertz for sub 6 gigahertz, whereas for millimeter waves we can support up to 400 megahertz also. And another key difference is the subcarrier spacing. As we know, all the modern communication technologies use the OFDM orthogonal frequency division multiplexing. In that, usually for the LT or WLAN, all these things uses the subcarrier spacing is fixed. Whereas to support the millimeter waves also, or to decrease the latency, the 5G supports the variable subcarrier spacing. And other thing is also is the ability to divide the bandwidth further more granular. So in a LTE, usually if 20 megahertz is present, the user has to decode all the 20 megahertz. Whereas in the 5G, it can be further more granular, can divide further more, so that if a device is present is not needs, it can decode only 10 megahertz, then it can be customizable to assign bandwidth part of 10 megahertz. So it doesn't need to decode whole bandwidth. So that granularity also designed in the physical layer. And other thing is to decrease the power consumption. In LTE, we have the for the synchronization or to get the timing frequency synchronizations, we have a specific signals like cell specific reference signals and PSS and SSS and PBCH. These are always on signals which consumes the power at the receiver side also. So yeah, to detect that. So whereas in the 5G, this number of signals, this reference signals are always on signals are restricted in this. Only SSB signal will be always on. Other than that, these PSS and SSS are self-specific signals are available. CSRS signals are available based on the user configuration itself. So in the LTE, we are supporting up to 6 gigahertz only, and whereas in the 5G, we are it does not support only 6 gigahertz. It also supports the millimeter waves up to 23 megahertz to 53 megahertz. And the duplex mode also, the duplexing mode is nothing but the downlink or uplink, which technology is used. Sorry, the TDD, in the TDD, usually if the downlink and for the uplink, same carrier frequency is used. Whereas in the frequency driven duplexing, only separate frequencies are used for the downlink and uplink. So in the millimeter waves, whereas in the FR2, only TDD used to increase the bandwidth efficiency. Um, so these are the frequency ranges supported in the LTE. Sorry, 5G. So let me go to the next. So here we will discuss about the how the 5G waveforms are present, and how the frame structure is present, what is numerology, and what are the other terms like carrier and bandwidth parts. We will discuss about that in this slide. Next slides. So in the 5G, there is a concept called instead of only supporting the 15 kilohertz, we are supporting the um, more than one subcarrier spacing. That is not only 15 kilohertz, it goes up to 960 kilohertz. It's multiple of 2 of the 15 kilohertz. It does support 15 kilohertz, 30 kilohertz, and 60 kilohertz. And these subcarrier spacing is refers to as a numerology. And then we will discuss about the how the frame structure looks like, the how the time domain duration, what's the time duration of the each frame, and how the frame is divided into slots, symbols, and subframes. And then we will discuss about the how to configure the carrier. If you want to generate a resource grid of the 5G, you need to give the information about carrier, how much resource are you are allocating, and we will discuss about the bandwidth part and how the resource grid looks like. So the key to many 5G features is the fact that subcarrier spacing in 5G can take not just one value, 15 kilohertz as said, but powers of two multiples of 15 kilohertz up to 960 kilohertz. As a consequence, as the orbital symbol duration is reciprocal of subcarrier spacing, the symbol duration also sinks. So in the top, you can see that this is the frequency domain, and this shows the subcarrier spacing. And at the same time, same number of subcarriers when spaced further apart occupies larger bandwidth. This is what can be seen as on the third line actually. The maximum supported bandwidth is for 15 kilohertz is the 50 megahertz, and it doubles if you increase the subcarrier spacing. If you take 30 kilohertz subcarrier spacing, it eventually increase the maximum bandwidth also. And there are other subcarrier spacings also I haven't included here. And in the next slide, I will show it can go up to 480, 960 kilohertz. And you can see the subcarrier spacing does impact your symbol duration. Means if you take the 15 kilohertz, it shrinks down your time domain samples also. This gives a low latency. If you increase, let us say if I take the 960 kilohertz, your symbol duration will be very low. So it will increase your you can accommodate more number of slots in a frame. So we will take a look into that to understand that concept. So this table shows the relation between the subcarrier spacing and frequency ranges. So even though there are multiple subcarrier spacing, the in the millimeter wave we are not using the we are not going to use the 1530 subcarrier spacing. because it will increase the, if you have used the 15 kilohertz in the frequency range 2, that is millimeter wave, which is the in the gigahertz, you will have the higher symbol duration, which will affect your Doppler also. Means if you have a Doppler, the 15 kilohertz cannot handle that kind of a Doppler. So in to avoid that cases in the frequency range, we use only 160, 120, and 240, and 480 and 960 kilohertz. And some of them not, the SS burst, some of them 60 kilohertz is on not used for the SSP, whereas 240 kilohertz is not used for the data transmission. It's only for used for the SS burst transmission. So in this slide, we will this is the time domain representation. Means how the time domain signal of the divided in the 5G. In the 5G, each frame is up for 10 milliseconds, and which is further divided into subframes. Each frame consists of 10 subframes. You can see that, and based on your subcarrier spacing, your number of slots per subframe changes, and each slot has symbols, 14 OFDM symbols per slot, and also because of the variable subcarrier spacing, the number of slots per subframe also is changes. So in the previous slide, we discussed one frame has the 10 subframes. If you increase the subcarrier spacing, how it is changes. If let us say, if I take the 15 kilohertz, it will have for each slot we will have for each subframe we will have only one slot. Plus, if I increase the subcarrier spacing, it will have the more number of slots per subframe. So it is two slots. Whereas if I increase to 60 kilohertz, it will increase by 2 terms, because it's and next for 120 kilohertz, it's increased by further 2. It's 8 slots will be present per subframe, and the symbols per slot will be constant, because of per every slot you will have only 14 OFDM symbols, and based on your subcarrier spacing, the symbol duration decreases. So this gives the actual understanding. So for every subframe, for every slot, if I take the 15 kilohertz, you can see that slot duration is 1 millisecond. If I decrease the increase the subcarrier spacing, the slot duration decreases, is 0.5 milliseconds. So 15 kilohertz slot will have the almost 2 slots of 30 kilohertz. And same as for the 60, you will have the 4 slots of 15 kilo. 4 slots of 60 kilohertz is equivalent to the 1 slot of 15 kilohertz. So now we will discuss about the carrier and bandwidth part. For each numerology, one carrier is defined. A carrier is characterized by subcarrier spacing, the numerology we have discussed, the number of resource blocks, and starting resource. To each carrier, an OFDM resource grid is defined. Means if you define a carrier, let us say here you can see the MATLAB code. If you want to define a different resource grid, you need to configure a carrier, and you can see there are two subcarrier spacing defined. One is 15 kilohertz and another is 30 kilohertz. Even though the number of resource blocks is double, they occupy the same bandwidth because the subcarrier spacing is double in the both of the cases. So next we will discuss about the bandwidth part, and this is how we define the carrier configuration in the MATLAB. Let us say if you want to generate a resource kit that you want to transmit over the air, or you want to transmit, you need to define carrier configuration. For that, you need to give the subcarrier spacing and what is the size cyclic prefix you want to use, and what is the size of the total grid, and which slot you want to use. And for that, if you want to get the resource grid information, you can give the NR OPM info of the carrier. It will give the how many number of subcarriers, how many which FFT it will be used to convert the frequency domain signal into time domain signal, and which samplet it will use, and what are the cyclic prefix lengths that will be used. Usually, the first cyclic prefix will be very high compared to other cyclic prefix lengths, and what are the symbol lengths, and all this information will be available. So now let us look into the bandwidth part. One bandwidth part is also characterized by subcarrier spacing and number of resource blocks and this starting resource. The bandwidth part is associated with the carrier that has the same subcarrier spacing, but they are generally usually in the 5G to support the users might have the might not support all the bandwidth, or he doesn't want to use the whole bandwidth. So the carrier bandwidth is literally sliced into parts, that is called bandwidth part, and based on the user requirement, that user requirement, a bandwidth part is assigned, and each bandwidth part is usually can be any user can have at most 4 bandwidth parts based on the subcarrier spacing chosen. Let us say if the user wants to have a want to receive over the 10 megahertz right now, and he wants to use in the next second or next time he want to decrease his bandwidth, then based on that bandwidth parts assigned, it can a user can have at most 4 bandwidth parts also, and based on his requirement he switches between the one bandwidth part to another bandwidth parts. You can see that um, how the frequency domain is divided into bandwidth parts. Here the point A is the reference point where the carrier is starts, and this resources are divided between bandwidth part 1 and bandwidth part 2. And next, as I said, based on user requirement, user can switch between the different bandwidth parts. As he can associate with the 4 bandwidth parts. First he selected the the user requirement is the low bandwidth. He used that, and they switched. The requirement is now higher bandwidth, and he switched to that, and back to the lower bandwidth. So in that way, 5G gives the granularity of switching between the different bandwidth parts. So as we discussed about the time domain till now, and here this is the gives the actual picture of how the resources will look like. In the OFDM, you will have the subcarriers divided. Your bandwidth is divided into subcarriers. This vertical direction gives your how the frequency direction, and in the horizontal direction gives the how the your resources are divided in the time duration. Means let us say user want let us say user has 20 megahertz bandwidth. It will be divided between the subcarriers. In the time domain, you will assign with the number of symbols, how many symbols he wants to use. So OFDM symbols and subcarriers you will combine together forms a resource grid, and this resource grid is shared between the multiple channels like PDSCH and PDCCH, and and other reference signals. So you can see usually in the 5G you have the resource based on the user requirement. the different kind of channels are defined. Means channel is nothing but if the user wants to have a data, usually it is shared in the PDSH. Whereas if you where these resources are present for the PDSH will be sent in another control information called PDSH. And other like all the control informations are other uh, common information across the users will be shared in the PBCH. All this divided in such a way that with certain rules. That is called the PDSCH, means that is called as channels. Whereas another parts are present which are used, which are synchronization signals. If the signal is received, we need to find where the signal starts and how the channel is present. That can be known by using the synchronization signals. So we have the channels and signals here, and I will discuss about. I will take an example of simulation like PDSS throughput CSA feedback simulation, and which parts are used in the simulation, like PDA. If you want to use transmitters use a signal, 5G use a signal over the over a channel, you need to configure PDSCH. And if you want to configure that PDSCH, you also need to know which modulation scheme you are using, which coding rate you are going to use based on the channel condition also. If the channel is worse, you don't want to use 1024 QAM on the for that user. So you need to know that channel state information also. So for the, if you want to use get the channel state information, you need to send a CSRS signal. This is a reference signal. It acts as a pilot, or sometimes it will give the another kind of information also. Once it is received by the user, it will user will send back some. It will do some um, do some calculation which gives the another report called CSI report, and this will send back by UE on PUCCH channel or PUSCH channel, and based on that information decoded by the GNB, it will configure your downlink data, means which modulations use, which coding rate it has to use, and in which direction it has to be sent. So we will try to simulate that. First, I will discuss about the what are the parts of that parts of the simulation. Like I will discuss about PDSCH and CSRS, and how the simulation can be done. I will explain the next slides. So, as I said, to do PDSH with CSI feedback, the user has to configure the carrier and PDSH signal and CSRS signal, generate the data for that. And PDSH signal, PDSH data you need to generate, and CSRS signal, and uh, configure how the channel you are, which channel are you going to use. This is the physical channel, or you can use the AWSGN channel also, and transmit, pass through the channel and do the synchronization and channel estimation and generate the CSI report. These last three parts are done at the receiver side. Um, uh, After generating CSI report, this CSI report is taken by the GNB and it applies to the PDSCH that transmitted by the GNB. So first discuss about the PDSCH. So first we will discuss about the before generating PDSS is nothing but a physical layer channel. Before that, you will have a user defined for the each user. You will have the based on your application, you will be generating some bits, right? So that will be given as a transport blocks by transport channel, and this and pass it to the PDSCH physical layer channel, where you will do the modulation and scrambling, modulation and interleaving and layer mapping as a part of the PDSCH processing chain. And then how these resources are allocated in the resource grid, and how the mapping types will look like. We will discuss about that. So this downlink shared channel is actually carries user data. It's in terms of the bits only. This will be present in the bits. It also carries other pieces of information like a system information block. The coding chain, includes the CRC attachment. Means once you have the bits, you will have the CRC. You will perform the CRC, and you will add the CRC, and code block segmentation part will be present. And this is very similar to the LTE, except the LDPC coding that will be different from the LTE to 5G. Remember this LDPC, this coding rate means based on your CSI feedback. Once you transmit the PDS, get the CSI report, this coding rate will be decided based on your CSI report. So then you will do the rate matching and code block concatenation, and it will generate a code word. So till here, downlink shared channel part till here still in the bits only. Then your bits are scrambled to get the frequency diversity, and then um, uh, these bits are mapped based on the modulation given by the CSI report, and then if the if it is a MIMO system, it will be based on your rank, based on the channel, how much user can support. It is mapped into different layers. This is also part of the CSI report. Based on your CSI report, the number of layers will be decided, and then pre-coding is applied. Then how the resource mapping is done, then the CSRS signal is added here to the PDSS resources, and the CSR is added together and mapped to resource grid, and this resource grid will be passed on a channel. So the previously discussed all this downlink shared channel part is nothing but this one. So here the user needs to know, the GNB needs to know the PDSH modulation, the number of layers here, and based on this modulation and number of layers, these parameters are is part of the CSI feedback, because as previously said, based on your channel condition, user has to assign with the modulation. And if your channel is worst, you cannot assign a different more number of layers to the user. So these pieces of information is available as a part of CSI report, and GNB will decode the CSI report. Based on that, it will assign these values, and then you can see once the configuration is done, you can generate the PDSS symbols for the given transport block, and then the PS DMRS, the DMRS also need to be configured to get the channel estimates for that PDSCH, and then pre-coding will be applied. The pre-coding is nothing but if there are multiple antennas to the on the GNB side, um, you need to steer that signal. You can steer the signal in the direction of the UE. So the pre-coding is nothing but it helps the GNB to steer in the direction of the UE. So in the modulation schemes for the LTE, it only supports up to 256 QAM, whereas in the 5G, it also supports up to 1024 QAM. In the MATLAB, you can simply implement this part. All this modulation in NR ODM modulate, NR symbol modulate. It will give the modulation part. So once your symbols are generated, if you have based on your, let us say if the user has the more than 4 layers, supports more than 4 layers, these these code word bits, code word symbols has need to be parallelized into the layers. This is nothing but the serial data is coming from here, the symbols that needs to be mapped onto the each layers. Let us say user supports only one layer, it's simple one. The symbol need directly serial to serial conversion. Whereas if the you user data supports up to two layers, the symbols are alternative symbols are assigned to the each layer. These layers are nothing but independent data streams that eventually goes to the precoder to for each antenna. And if there is a one code word based on one code word only generated, and if the user supports three layers, it till four layers in the with the one code word. It is simple. It is directly serial to parallel conversion. Alternative symbols are transferred to each layer. Whereas if the more than one code word is present, so if the your number of layers is more than four, it will be that two code words will be divided in such a way that five layers in the five layers, first two the first code word is shared as the first two layers alternatively, whereas in uh, the next code word, second code word is are parallelized into uh, another three layers. Similarly, for the six layers, it will equally divided between first code word will mapped into first three layers, whereas in the second code word it's mapped to next three layers. Yeah. So after one or two code words got mapped to between the one and eight layers, the layers undergo the precoding, which is interestingly not specified in the standard. Actually, precoding operation is maps the layers to the as many as more antenna ports using the matrix multiplication with the precoder. Let me put the PDSCH also mapping. It supports two types of mapping compared to LTE. That is a type A and type B. Type A is nothing but PDSCH takes whole slot, whereas in means 14 OFDM symbols. Whereas in the mapping type B, it only takes a partial part of the slot. You can see the in the type B, it is consuming only the 10th and 11th and last four OFDM symbols. So yeah. So the if you see in the resource kit, the the two examples for the type A and type B. User needs to configure these parameters if you want to use the different kind of PDSS mapping. So this one is type A, and in the same resource kit, another PDSH is defined, another data is assigned to the user, that is type B for the other user. To configure that in the MATLAB, you need to assign these parameters. So once the on the receiver side, user receiver doesn't know where how much data is present for him, and GNB also doesn't give the total information. Like for each user, it doesn't give that this much of block size, transport block size is assigned to you. it gives the piece of information, because if you give that information, it will be overheaded for the users. So it is signaled in the form of three parameters, like modulation coding scheme. It will be known at the receiver side in the form of TCI, and the how many number of resource blocks will be assigned to that user, and what is the overhead is present. With these parameters, user will calculate how much resources are present from where to where. From the modulation coding scheme, he will know how many from the how many symbols are let us say if he has 1024 form, he might be he will have the 10 bits, and whereas with the help of coding rate, he will get the actual information, how much length of information is present, and with this he will get to know how much length of data is assigned to him. So in the previously we discussed about the for PDSS CSI feedback, we discussed about the how to configure PDSS signal, and to know the user's channel conditions, he needs to send the one sounding signal that is called CSRS signal, and this CSRS signal at the UE will calculate the channel based on this CSRS signal, and he will perform some operations to estimate the channel, and these parameters will send back to the GNB as a form of CSI report. So we will discuss about the how the CSRS signal, how the CSRS resources will be assigned, how it will be configured in the MATLAB. So channel sounding can be done in two ways. For the TDD, if the uh, user the GNB doesn't need to have a feedback, because the for the uplink or downlink we will have the same frequency is used. So this properties for the channel is called reciprocity, means the same frequency used, the same channel experienced by the transmitter and receiver, you can only the direction will be reversed. So in that cases, if the TDD is if the TDD mode, the 5G uses TDD mode, then only one transmission is needed. There is no need to give the feedback need to be present from the um, CSI feedback has to be present between the user and GNB. For this, to get that, let us say UE transmits one signal that is called sounding reference signal. Is sounding reference signal, GNB gets the channel for uh, based on the SRS, and this can be used for the downlink also. It interpolates the channel coefficients, and it will use for the downlink data also. This one way, and the another is the if the FDD mode is present, or TDD also, the CSRS signal will be present, will be transmitted from the GNB, and GNB and UE will receive that signal, and it will provide the CSI report as previously said. And this it will be based on feedback. It will beamform the signal and code the modulate the signal on the PDSCH and code rate the signal. So CSRS is not only used for the downlink channel sounding, it also used for the CSI reports I previously said, and also used for the tracking reference signal, phase tracking to phase track the PDSCH, and this is very similar to the cell specific reference signal, but it's very configurable to the based on the user need, um, and it also supports the more number of antenna ports. And also this CSRS signal also can also be used for the interference estimation. There's in the CSRS signals, there are two kinds of resources are available. One is the NZP CSRS, and another is ZP CSRS. ZP CSRS is nothing but at that locations in the resource grid, uh, nothing is transmitted. Means in that locations it will be nulls, and it in that location, if there is an interference is present from the other cells, that will be captured by the receiver, and it will estimate the interference at that locations. So the CSR signal can also be used for the interference estimation. So, and this CSR signal is specific to the bandwidth part. It will give the if configure for a specific bandwidth, it will give the channel estimate for that specific bandwidth part. As discussed, the zero power CSRS, if the serving cell is configured with the zero power CSRS, you can see the in the middle part there is in these locations the GNB doesn't transmit anything. So the interfering signal cell will be captured in these locations, and UE will estimate how much signal strength is present in these locations, which is specifically only the interfering cell signal strength. With this, you can calculate the interference signal power and use it for your all the CSI report, or you can see based on that also, if the user is at the cell edge, you and if there is an interference present, the CSI report given by the user also may not be proper. So assigning the 0 CSRS signals will give the interference strength at that location. Based on that, the modulation also will be adjusted based on the interferencing power by that UE. So to configure CSRS, you need to define which kind of resource you want to use, ZP for the interference estimation and non-zero P if you want to use for the channel estimation, and how frequently it will the periodicity of the CSRS signal. And the density is nothing but how many CSRS resources has to be present for each resource block. One means for every resource block there will be a one CSRS resource will be present. If it is dot 5, even it is like for every two resource blocks, the one CSRS signal will be present. So the number of antenna ports supported by the CSRS signal depends on the row number you're chosen. There is a table defined by the 3GPP. Based on that, if the user wants to get the information along the different antenna ports, he can increase this row number or configure according to that. So based on your user's bandwidth part, the symbol locations and the subcarrier locations has to be modified. So till now we discussed about the GNB will transmit a CSRS signal, and UE will at that location she will do the channel estimation. Based on that, it will give the CSI report. There are CSI feedback. This CSI feedback contains specifically mainly three parameters that will be useful for the configure the downlink data. That is rank indicator. Rank indicator is nothing but how many number of layers that UE can handle here. If the user can handle two layers in his condition, then the rank is indicated will be as 2, and PDS is configured in such a way that if there is two layers it can assign to that user, GNB will assign that 2 layers of streams as previously discussed. The number of layers will be assigned based on that rank indicator. Another is the channel quality indicator. This parameter will give the which modulation scheme it has to use and which coding scheme has to use. So if the user channel is worst, he will decrease his modulation index, and he will go from the 1024 comma 64 com to QPSK to get a reliable signal. So you will report my channel is worst, and you need to decrease your modulation scheme so that I can get the reliable signal. And to correct the signal also, the coding rate has to be increased. So modulation and coding scheme together will give that information. So this is given as a part of channel quality indicator. Another is the based on user direction, GNB has to steer the signal, right? So the the precoder is nothing but based on direction. It will give that matrix that has to be multiplied by the PDSA signal. Um, so that matrix is the set of matrices available in the defined by the 5G standard. The is called codebook. Based on user's direction, that precoder matrix is selected from that set of precoder matrices available. So this precoding matrix indicator will give the information about that. So for each parameter I said, there is a selection process for that. How based on different parameters, each parameters has to be is selected. For the precoding matrix indicator, um, in the user side, it will user will have the channel estimates available with him, and he will have the set of precoders that are supported by the that needs to be supported. So for each precoder, it will multiply with that channel and the precoder. It will calculate the SINR for each precoder matrix available. Whichever precoder matrix gives the highest SINR, that precoder is selected, and that precoder matrix is indicated to the GNB. Similarly, after calculating the SINR values for each SINR values under that precoder, on the UE side, he will have a SINR table. If this much SINR is available, how much throughput he can support. So for each modulation scheme, user will select each modulation scheme and coding rate, and for this SINR, how much throughput he can support. Whichever modulation and coding scheme gives the better block error rate, if the lesser block error rate, that channel quality indicator is selected and indicated to the GNB side. And next, the addition on the number of layers, how many number of layers a user can support based on PMI selection and CQI selection. Know the which modulation scheme we can use, and which precoder we can use. With this information, we can calculate the uh, spectral efficiency for each parameters, like for each number of layers supported. Let us say user has the GNB has 8 antennas, and UE has 4 antennas. It can support up to 4 layer. At max 4 layers it can support. So for each layer, we will calculate the spectral efficiency with the CQA values and precoder PMI values, and whichever layer gives the highest spectral efficiency, that is selected as the RI. So the number of layers that user can handle, the receiver can handle, that is indicated. These three parameters indicated back to the um, GNB, and then GNB will take the suggestion from all the users, and based on the user, if the it can accommodate how many number of users are present. If the uh, out of 10 users it can accommodate, then it will select that users CSI feedback and assign according layers according to that, and modulation according to the CSI reports given by the users. So till now, we discussed about the carrier to generate the PDSCH, to do the PDSS CSA feedback. We need to generate the PDSS signal, carrier signal. We need to give the information about the carrier, and then we need to give the information about the CSRS signal. And all these parameters needs to be configured. So first, we need to configure the. We have the in the MATLAB. We have the NR carrier config, which gives the information about resource grid. And the next, the for the specific user, which data how the data has to be present, can be done using the NR PDSH config and NR PDSH DMRS config. As you want to use the CSRS signal for the CSI feedback, you need to configure a CSRS config, and how the information has to be present means for every the periodicity, all this and how the what are the parameters that needs to be reported by the user. That information will be available in the CSI report that needs to be configured. And next, you will generate the bits and the symbols. Based on bits, you will generate the PDSS symbols and DMR signal symbols and CSRS symbols, and this will be mapped to the resource grid. So all this process can be done in either programmatically or app also. I can show you the app how you can configure. Till now we have seen what are the there are for each function you will have around 5 to 6 parameters at least to configure that. You need to write program for that. In the there's an app called wireless waveform generator in the provided by MATLAB, which gives the UI. Users can easily set their parameters for that their desired configurations and generate the signal 5G signal and use it that for your transmission. You can generate the script for that configurations also. This is how the app looks like. So let me show you one demo on how to use the wireless waveform generator in that. Let me start that. So here you can see to perform PDSS throughput and the CSI feedback with the CSI feedback, we need to configure these parameters: downlink, shared channel, and PDSCH, and then perform the pre-coding matrix pre-coding based on the CSI got from the CSI report given by the user, and then configure the channel model. And this part, all of them, you can see it here, the generation. First, users to simulate that, user need to configure the carrier here. And then provide the how your antenna panels are present. And configure CSARS as previously said.
Sir, I think your screen is stuck.
Are you able to see it? It's
Uh,
still blank.
No, no. It's showing the files, list of files, bit streams.
Some files are showing build underscore
Okay.
VT string.
Okay, I think I need to change the different one. Let me change the shape. Can you see it now?
Yes, sir. Yes, sir. Thank you.
Okay. Thank you for that. Let me. So to configure all these, till here you can see user has to write at least configure all these parameters to generate a signal itself. So this all these things can be done easily with the UI. Let me start that. And the other thing is when you writing a program on the MATLAB, you want to configure carrier and PDSCH, all these things. All of them has to be in sync. If the resource block of the resource block assigned for the one carriers is not matching with the PDSCH, you will get errors. So simulating that is kind of painful. So you can actually MATLAB directs you to the how to configure what are the issues present based on your configuration. But UI does much more than that. It will guide you. So let me generate a signal that is same signal that present in the example previously as shown. So I want to generate a downlink waveform signal. So I took the downlink here, and in that, first I will give the what is the carrier configuration that needs to be present. So let me pull down this. So I want to use the subcarrier spacing of 30 kilohertz, and I want to use only 52 resource grid size. You can see if I take the 30 kilohertz and 270 resource blocks, I need to have an issue with the number of resource blocks that I assigned here. So the app guides me in such a way that I need to configure some other parameters also. So I just need to update this. And I don't want to for this simulation I don't need a SSP here. So I'm just disabling that SSP. And another configuration, first we we configure the carrier as previously discussed. You can see carrier configuration. First I configured that carrier configuration. Then I need to configure the PDSA signal that I want to transmit. So here you can see for the carrier, I only said I have only 52 resource blocks available. So your PDSS also needs to be modified according to that. So your VRB set need to be modified. So app guides you in such a way that uh, you will only have this one. So or 52, 0 to 52 is a 51. So and I don't want to have any PDS CCH in that information. So I will remove that. And in the CSARS signal, I want to have a specific, I want to enable CSARS signal for CSA feedback. I want to have the different number of support different number of antenna ports. Let us say 6. So for this, I need to, if I take the 6 number, I need to update the symbol subcarrier locations also here. So subcarrier locations is here is nothing but if you see the CSR, there will be a table that defines all these things, how it needs to be configured, means what are the parameters supported. So in the you can see the resource grid here actually. So in this resource grid, I have only PDSCH, CSR signal present and mapped to the resource block. And there is no error here. I will just generate the signal. And you can see the how the your spectrum looks like with that resource blocks and your configuration. And if you want to generate it as many times you want to, you can get the code for this also. You can directly do the either you can save it to your file or you can directly do the export. The export does the saves to your workspace, or you want to export to MATLAB script will write a MATLAB script for you, so that you can use this program somewhere you want to use. So here you can see the MATLAB script that is generated just now. You can see that it is generated just now. So all the carrier configuration, subcarrier spacing, bandwidth parts, and how the SS burst will be. You can see it is false. It's known. It starts with the default configurations, and how the PDSS configuration has to be present. And use it for your simulations. And also there is another once you generate it and pass through channel, and you can analyze your received signal in another app called wireless waveform analyzer, which till now the generator part is how to generate the signal. Analysis is nothing but he gives the how the your signal is looking, the receiver signal is looking. So if you give the what is the configuration of your waveform received, then it will do the all the analysis like EVM, and how the spectrum is looking like, and what's the constellation. So with the default one, let us take configuration. One configuration demo configuration is already present in that. So it will show you all the which bandwidth parts are available, and for each bandwidth part how the EVM is present, and the how the spectrum is looking for that signal, and the constellation. And also there are other couple of examples to get started with in the 5G. That is like beam. You want to do the beam forming, CSRS beam forming, beam management, and in the system level you want to simulate if more number of users in the system level. MATLAB Toolbox provides that too. So with this, my I will conclude here.
Thank you, sir. Thank you for such a wonderful session. Can we take questions from participants?
Sir, I
Now-
have the one query. Can I ask?
Yeah.
Hello, am I audible, sir?
Yeah,
Yes,
I can
yes.
hear you.
Sir, can we classify these CSAP means channel state information with respect to the services, whatever the services are available, different services available in the 5G network?
So different services, for example, can you give the examples on that?
For example, there are 10 users that are availing the different services. Some on means web browsing, some of having the live streaming data. So
Yeah.
depending on that services, whatever the services they are availing. So can we decide, or can we generate the profile with respect to the CSI?
Yeah, you are so let me break it down. So let us say you have multiple users are present, right? Based on users, you will have let us say one is using for the multimedia service, one is another device is present that wants to communicate,
Yes.
another sensor device is present. These
Yes.
two are generate bits,
Yes.
and these bits will then mapped into symbols in the
Yes,
physical
sir.
layer. It doesn't differentiate between this one is the this bit has to be served, this bit not to be served. What it does is based on users information. Let us say user it will transmit the CSRS signal to the user. Let us say this UE who requesting for the multimedia service will request I need how the channel I need CSRS signal. So GNB will send the CSRS signal, and based on his conditions, means if it is a very corner which doesn't have a proper signal, the UE will perform, whoever the device will perform the operations. It will give the channel estimation of that based on channel between the users, and this UE will give the feedback to the GNB itself. Based on that, whether he will be served as whether he can take, let us say for multimedia service, he needs to have a higher modulation schemes. So
Yes.
if his CSI channel is worst, he cannot assign with the 1024 QAM higher speed. So
Yes.
in that cases, it will be assigned with the QPSK. So based on users CSI report, the GNB will decide whether which kind of a modulation schemes or which coding rate it has to be present. So yeah, so
Yes.
it is more like based on users CSI report, the GNB will decide whether this kind of communication, which kind of modulations and the coding scheme it has to be assigned.
Yes. Sir, do you have any data set in respect of this CSI?
Yeah, so this previously I shown one examples, right? This is an example, PDCS CSI feedback example. This, if you go 5G toolbox, if you go to 5G toolbox and if you open an example called 5G. So this one only actually. So here it gives the this simulation is nothing but this is one UE and one GNB communicating together. So how
Okay.
the channel is present, and if I increase this modulation scheme, how the throughput will come. If you simulate this, you can see at the end with the increasing the SINR, how the throughput is increasing for that user. That information uh, is presented here. So how the precode is configured, how the modulation is configured, all the data is available in this example. So you can see it here. If the user, if the GNB uses the power of minus 10 dB, means it is like the SNR between uh, the signal to noise ratio is minus 10 dB. In that case, you can see the throughput that users is going to get is around 8.45 Mbps.
Yes.
Whereas if the power is increased, means if the is channel condition is better, then you can see the
Improve.
modulation is improved, and it is using more number of layers and
Yes. Yes.
transmit code rate. So eventually, that user is served with getting throughput is increased for that user. So from here to here, you can see the throughput is increased.
Data
So
rate.
this, yeah, you can simulate that in this example. Yeah,
Yes.
this is for
So,
the yeah. Go on.
so please share these resources so that I can explore more.
Yeah,
Yes,
sure,
sir.
sure,
Sir,
sure.
after the session, definitely we'll share to everyone, sir.
And please, sir, your share contact also. If any further doubt, I can contact.
Yeah,
Thank you, sir.
yeah.
Sir, I have doubts, sir. Sir, actually here assigning bandwidth parts or assigning modulation scheme to the user completely based upon the channel conditions. So can you explain how can we calculate this channel conditions? Like how can we estimate channel
Yeah,
by considering what parameters?
yeah. So i- uh, there is a CSRS signal. There's two kind of signals are present that GNB transmits. One is the CSRS signal. This CSRS signal known at the GNB and the UE side also. So UE knows that this kind of signal present in my received signal. So at that locations, it will do the channel estimate, and it will get to know how, okay, my channel at my channel is present in this way. So based on that channel, it will do some calculations. I shown that that PMI selection, CQA selection, RI selection. So it will perform that, and based on that, there's another example also. You can clearly go, gives the how it is done each parameter. So NR Downing says a reporting example.
Sure.
So which gives the how the modulation based on channel estimates and users location, how the precoder is selected, how the CQI. CQI is nothing but modulation and coding scheme, how it is selected. All this information is present here. So you can see it here. The how the code books are nothing but the set of precoders.
Yes, yes.
And in the CQA selection, it will do the for each modulation and coding scheme how the block error rate present. So there is a table in the UE side itself. So if I use this kind, if I my SNR is this much, and if I use this modulation and coding scheme, how much block error rate I will get. So
Okay.
based on that block error rate, it will decide. Okay, if my block error rate is very high, it will say that I won't use that modulation and coding scheme. So this information is passed to the GNB. Based on that, it will decide which modulation coding scheme is present. So you can go through the inside parts of this example also, how that actually functions. So you see it here. The for each HCQA select, H downlink PMI select, and
Yes, yes.
HRA select, each gives the information about that.
Okay, sir. One last question, sir. So for
Yeah.
5G simulation, actually, which fading model will you consider, sir?
It,
Or we need to consider?
Yeah, there are a couple of channels defined by 5G standard itself, which is called as NR channels, CDL and TDL channels. So, and they define how the profile looks like also. So you can go through that too if you want to simulate that. For this example, you can see only I think in this example NR CDL channel we have to took here. TDL channel. So no, sorry. The TDLC channel model is took. Uh, we can use NR serial channel model also based on the user's use case. And if you want to simulate a very system level simulation also, we have 38.901 channel model, which means it will simulate more number of users are present in a one and four number of GNBs are present. It can simulate that. So
Okay, sir.
yeah, if you go to let me give that information here itself. As already previously someone is asking about where is the locations about this. So if you go to 5G box and just I'm googling it here itself.
Sir, please zoom out your screen.
Okay, zoom in. Is it zoom in? You are asking?
Yes, sir.
Yeah. So here itself you can see what kind of informations are available. If you want to generate a waveform, what are the things you need to configure, and how the each of the parameters will be done. And there are examples for each of the simulations also. So, for example, someone is asking about the you are asking about the channels also, right? So I think somewhere here there will be a functions explaining about the different kind of channels that is available that you can use for the 5G simulations. So if you yeah. Yep. I can give you the link. If you go it here, you can easily take a look into the what are the examples are present, what are the functions present to generate a 5G signal and use
Okay,
it.
sir.
Yeah.
Sure, sir. Sure. You share. So after the session, you share it, sir. I will forward to the participants.
Sure,
Sir.
sure. Sure.
Sir, please share your contact.
Yeah. I will send it to the Madhukumar sir, and you will.
Sir, I'll forward it to sir. Definitely after this.
Okay,
I'll
sir.
share.
Okay, sir. Thank you.
Sir, thank you, sir. Thank you.
Yeah.
It's very gratitude for delivering such a wonderful session, sir. Sir, your expertise in software-defined radios and 5G technologies combined with your practical explanations, so has provided us with valuable knowledge, sir, and deep understanding of cutting-edge technology, sir. So thank you very much, sir.
Yeah. Thank you. Thank you. It's pleasure is mine.
Sir, thank you, sir. Thank you, sir. So, dear participants, so now we are moving for the next session. So already Govindacharya sir already joined. So long back by 7:30 itself. So thank you, sir, patiently waiting. So Kalyan ma'am,
Yes, sir.
now I request Kalyan madam to introduce today's sixth session's esteemed speaker.
Yeah, shall I start, sir?
Yes, ma'am.
Yeah. A very good evening to one and all. This is Kalyani, Assistant Professor from the Department of ECE. So it's a great privilege to me to introduce today's guest of honor, P.A. Govindacharya sir. Sir has completed his BSc from Andhra University in 1968, MSc Physics from Andhra University in 1970, and sir has completed his PhD in Engineering, ECE Department, in the year 1976 from Indian Institute of Science, Bangalore. Sir is having 38 years experience. Among 38 years, 22 plus years in semiconductor industry, VLSI and MMICs. Sir worked as professor in ECE department at Vasavi College of Engineering from June 2004 to 2019. Sir had taught VLSI related subjects such as VLSI technology, VLSI design, etc. to Master of Engineering students. Sir has guided many projects in VLSI area from 2004 to till today. Sir is also worked as Executive Director in Semiconductor Complex Limited, GATEC Project Hyderabad from November 1995 to June 2004. Sir had also worked in Semiconductor Complex Limited, R&D, Chandigarh from 1982 to 1995 in technology development, which is responsible for developing 3U CMOS, TU CMOS, E-square Pro, CCD, etc. technologies. Sir also worked as a research associate at Indian Institute of Technology, Kharagpur in Material Science Center during January 1981 to October 1982. And Sir also worked as research associate in Indian Institute of Science, ECE Department, Bangalore from 1976 to December 1980. Sir has published over 30 technical papers, and Sir is also a membership of societies, fellow of IETE, and senior life member of IEEE. Sir presently working as a director at Manjeera Digital Systems, Gachibowli, Hyderabad Education. Sir, it's a great privilege to us to have you among us, and I just hand over the session to P.A. Govindacharya sir. Thank you, sir.
Sir, Govindacharya sir. Sir, are you there? So participant, just a moment. Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir. I can hear you, sir. You can start, sir. Yes, sir. I can hear you, sir. You can start, sir. Sir, I can hear you, sir. You can start, sir. Sir, I can hear you, sir. You can. Sir, you're on. Yes, sir. Yes, sir. Here I can hear you, sir. Sir, I can hear you, sir. Sir, you unmute yourself, sir. Sir, unmute yourself, sir. Unmute, sir.
Okay. Hello.
Yes, sir. Yes, sir. We can hear you, sir.
Yeah. There was some problem with that. Okay.
Yes, sir.
All right. Thanks for the introduction. Okay. I am are you able to let me see the screen.
Hear you, sir.
How do I share the screen?
Sir, there is an option at the bottom.
Yeah, right. Okay.
Yes, sir. Yes, sir. Now it's visible, sir.
Visible. Okay, fine.
Yes, sir.
Okay.
Sir, if possible, make it full screen, sir. Maximize it.
I'm going to do that. Okay. Okay.
Yes, sir.
Okay. Thank
Perfect,
you.
sir.
Thank you. I am Govinda Charjulu. I am a director at Manjira Digital Systems. I'm not really into 5G technology. Okay. But I'm going to introduce to you a very special processor which has been developed by the Manjira Digital Systems, which is a universal multifunction accelerator. This is for a high performance computing, which can be used in most of the applications. It's a data plane processor, performance of a hardware accelerator, and the beauty of this is that it is a very unique processor which is used for acceleration. Okay. And then most of the hardware accelerators are in the form of ASICs. You cannot modify once given for a particular application. You cannot change it for this one. Whereas this is a programmable processor. You can run any algorithm without changing the structure. So that is the beauty of this particular processor. Okay, it's a vector processing engine. It's called middle stratum operations. Okay, which will explain in a few minutes what it is. And it's a application specific signal processor with unprecedented performance at ultra low power. It has got very low power, programmability, and occupies very small silicon area. It has advantage in all these directions. This is what I'm showing. Okay, what you like to have is a high performance, low power consumption, high programmability, and a low silicon area. There are the various things. CPUs performance is low, power consumption is high, programmability is high, of course silicon area is low. When you come to custom GPUs, the performance is medium, very high power consumption, medium programmability, and very little larger silicon area. Come to this, we have very high performance. How it is done is a new computing paradigm technology that has been developed, and it consumes very low power, and it has very high programmability and low silicon area. Okay, so this is the basic advantage of this processor. Basically, we call it universal multifunction accelerator. This is the structure I will explain in a minute. These are uses what is called multi-stratum operators, MSOs, multi-stratum operations. Basically, it is a combination of mathematical and logical operations are concluded. It is a data access is also provided within that, and uses small granularity operations and that are runtime programmable. Okay, the vector process engine. Okay, operations. One advantage of these operations is within the local memory. It is a pipeline architecture and then generic interface. Most of the time, you put your data somewhere outside in the memory, then you need to bring it into the processor. So during that process time, lot of time is wasted. So then your efficiency comes down. Whereas in this particular structure, what you have is there is I will explain the architecture in a minute. Okay, it is a in-memory computing data path architecture are realized in a viable processor. So the data access bottlenecks are removed and high performance and therefore low power consumption happens. Control, basically the processor, I will explain to you in a minute, the control flow is moved to a small microcontroller. So software programmable and easy to use. And optimal parallel architecture, low silicon area and high MAC efficiency, multiplication accumulation. Modular design is seamlessly scalable and highly customizable. Okay, you would see that this is the basic UMA system. You have a computing engine, and then it has got a local memory, and there is a control flow engine, what we call CFE. This controls the whole process, and then it also passes the operations to that, and then uses, and the operations are done. There is a local memory for the system. Okay, this is so that the transfer of the data from here to the engine is very fast, so it doesn't depend on the external memory. That's what makes it faster and much more efficiency. This is called multimedia data plane processor, or simply known as MDP. MSOs, I will explain what they are. Issued to the UMA through this CFE, and on the local memory it operates, and it is seamlessly scalable. What do you mean by seamlessly scalable? Will come in a minute. Now, any multimedia algorithm can be represented by in terms of a small set of MSOs or middle stratum operations. Basically, this is each of the MSOs is a small algorithm itself. Okay, so your the becomes more efficient. So then any algorithm can be programmed in terms of MSOs and runs on CFE. So this makes it very advantageous. Suppose you have some kind of algorithm which you want to implement, use these MSOs that are defined for this and create your program and run it on the UMA. So therefore, whether you say the SP processor or any other thing, so which you don't have to change the processor or the architecture to do the operations. So this makes it very, very advantageous. Okay, and we have generated a number of MSOs for this. MSOs, let us say, like addition, subtraction, FFT, all those kinds of things. There are about a large number of MSOs that are available, which can be used for achieving any algorithms. Okay, so a function for any new multimedia algorithm can be easily developed using MSOs and then included in this library, and then any algorithm can be fitted onto this, whether it is, as I said, a DSP operation or any other similar very high complexity computation involved algorithms can easily be implemented on this. Okay, so the MSOs are special instructions specific to this processor and is a combination of mathematical and logical operations, and then instructions for configuration and utility. All these things are there. These are what is known as a tiny algorithm by itself. Let us say you want to do some addition. So you take two numbers and then these are completed and then stored into the memory. So the algorithm of addition is run in one cycle. You don't have to don't have to fetch the information, you don't have to compute, and you don't have to store it in the memory as separate cycles. So single cycle, it can do that. And similarly, it can be done for any of the other operations. Data access, I said, and these are configurable on 5 and generic for application. They don't have to program it. Okay. So amenable for parallelization. Okay. And then new MSOs can be added based on the application requirement. Therefore, because of this very high raw processing power, high acceleration of complex algorithms, ultra low power consumption, high degree of programmability, and future readiness. That's what I said. You don't have to change the processor depending on the application. Only you make it bigger and bigger system by expansion. I'll explain to you that in a second. And seamless scalability, reduce the data traffic on the system bus. This is what I said. So on the data traffic on the system is reduced immensely so that your processing time is done, and then many number of operations can be done. Easily programming, simple integration to any SoC, a system on system, on chip, and high degree of customizability is the advantage of this system. You can see that here. What I meant by configurability, this is the nomenclature of this. This is called MDP, that is already told you, that is multi-data processing. Okay. Then you can have the UMA cores, and then as I said, it is a vector engine. So you have the vector engine, number of cores that you can have, and then based on that, you can build the entire system. So for example, if you have a 32 vectors, okay, and then each a core of 16 cores of this 32 cores. So that's what makes it a very highly processing engine. Okay. Again, same, you have the local memory on which the operations take place, and then the configuration can be done. If I want something else, I will show you in a second another configuration what we are presently using for certain applications. That is something like MDP 8v2. That means 2 cores and vector length of 8. So that means 8 parallel the MAC operations, other things are done 8 different places. And then the local memory can be properly organized so that you can addressing problems and other things are very easily addressed. Okay, an example of this particular thing, this, and as I said, is a small area that is at 28 nanometers node. It takes just 24 millimeter, all this complexity, including the local memory. And the core power is 80 microwatts per megahertz of operation. Okay, so then if you look at the operation at 1 gigahertz, that is the frequency of operation, you can go to teraops kind of thing with 16 or 8-bit 8 configuration. So example, if you have a 2-dimensional filter on 2 multipixel megapixel image, it can complete in 33 kilocycles and with a operation of 1.08 tera operations. Okay, and then it can easily be integrated into any system. So you have the basically host processor, there is a system, there is a MDP, that is the data processor, and then you can combine to other processors. Okay, then you have RAM, that is system memory. The internal memory for this is different from this, so you can store the data and then from there transfer the data onto this MDP at one time, complete the operation, and then store it back. So the whole thing doesn't take much time. And you can have other peripherals in the that are connected to any of these peripherals what you need to connect. Okay, like UART or any of these things can be connected. Okay, and there is a storage UMA library. Algorithms ported on UMA are stored in the memory, and required algorithm is loaded onto the MDP. That's how it operates. And then because of this specific structure, it becomes high performance and programmable SOC. That is the basic advantage what you have. Okay. So, and very easy to implement this. Okay. You have an application, okay, which can be configured in terms of the MDP libraries, and then you have the host, and then this is the hardware, there's a kernel, that is the OS that comes into this one, and then the whole thing, other devices can be connected. It's very easy to implement into any of these SOC systems. Okay, so you have the user application. Basically, what you do is you write whatever algorithm you want to do in terms of a C language with MSOs incorporated into this program, and this can be transferred onto the UMA processor. Okay, so what you have is input data and user application, and then the model is converted into the UMA primitives, and then from there the acceleration takes place. Okay, so it's a very what I would say high efficient, low power, and then configurability, that is the most advantageous. Okay, so now there are certain applications that have been developed on this, based on this. we have given this to ISRO for the image processing, that is the SAR image processing. I would like to tell you that here they have this is put on an FPGA, okay, and then the ISRO was using GPUs, a lot of them, consuming more like about about more than 1 kilowatt of power, but still not able to achieve the real-time one. Whereas with a small J-Links FPGA, we understood the algorithm, what they wanted to do, ported onto the put the UMA processor on the Xilinx FPGA, and then ported the program onto this, and were able to achieve very simply the synthetic image processing. Not a very simple. Okay, it is a 2-core subsystem for ASIC, that is a baseband processing. We also have developed a NAVIC receiver module for navigation purposes. And then we have given this IP to Intel for their hyperspectral camera processing, and for Altera FPGA server acceleration and AI. And then NXP, that also we have given for the data communication. And then in the next immediate future, we are coming to another next generation processor for AI, artificial integration, as well as possibly for a 5G application. Okay, this is what we have done for the NAVIC receiver. Okay, the baseband processor, which we call MDP, the DB01, it has 2 MDPs. Okay, each of the MDP has got a vector length of 8 and 2 cores of UMA. So there are 2 such MDPs, and then with that we are able to receive the signal from the satellites, and we are able to do the position computation and things like that. So this is the running the NAVIC algorithm, and also GPS algorithms have been done. Okay, so this is the one which is being right now ISRO SAC Ahmedabad has tested them, found to be working all right. So we have developed this system. This is the sum of what we have been doing. Okay, we can have all AI inference accelerators are built with UMA, well-rated on FPGAs, fabricated a baseband processor, what we call DB01 at 28 nanometer node, which we are using for the NAVIC GPS receiver. Okay, and then we have partnered with, as I said, Intel, and then we have the right now we are working on the next generation processor for this one. Okay, so then we can provide IPs for ASICs or FPGA, silicon for AI and DSP applications, and both with associated software, because the software, as I said, uses the MSOs. These are the specialized instructions on UMA. So these ones need to understand this and then implement, and the whole thing becomes very easy. As I said, once you have this system, you don't have to have the hardware knowledge of this whole thing is not needed. What all you need to know is that understand the UMA MSOs, and then implement your algorithm using them, and then you can run on the accelerator. Probably that's what I have. I'm sorry, it's a very small preparation. I was away for quite some time, so that I was not able to make a full justification what people wanted for me on this. Okay. Thank you.
Thank you.
And any
Thank you,
questions
sir.
on this will be done.
Participant
Yeah.
can ask any questions. Sir, in the context of 5G, can we relate it, sir?
Pardon me?
So, in the context of 5G, can we relate this more?
Yes, yes. See, most of the time, what is 5G? Uses a lot of algorithms for data reception, computation, and then transmission, right? Right?
Yes, sir. Yes,
So
sir.
all these algorithms can very easily be implemented on this.
Sir.
Okay. So actually, we are designing the next processor, which can, of course, the here right now, the one what we have silicon fabricated is not a very big one. It has limited capabilities, but the next generation processor will be able to address this kind of 5G applications. In fact, we have a plan to do that.
Thank you, sir.
Yeah. Okay. Any other
participants? Do you have any queries? You can.
maybe it's a little, if you have, you can send it to me, because something is different from routine. You may not have immediately any questions. So you can, any clarification you might send to me to my address. Okay. All right. I'm sorry, I have not taken much time, I hope. Yeah.
Sir,
yeah, please.
Sir,
go ahead.
And so in deep with practical explanations to this UMA is very helpful to us, sir. When we will focus on this side also, sir. How can we incorporate this UMA in the context of 5G, sir?
EMA.
Thank you, sir. Thank you, sir. Wonderful.
Okay. Yeah. It can be done. See, as I said, essentially any of the algorithms can be incorporated in this. Now, if you look at the GNSS NAVIC receiver, we have a RF front end,
Yes, sir.
and then from there signals are taken, and then from there the algorithm processed inside this one. Okay. Now take the case of 5G. You might need to do a beamforming, etc., right? So essentially, the beamforming is itself again another algorithm, right? So what you need to do is you have the RF front end is separate from this basic processor. From the RF front end, control will come through the processor. So that's how the whole thing will work.
Yes.
Beamforming or the what you call the data extraction from the transmitted data, down conversion, other things have to be done at the RF front, as in any system.
Sir.
Yeah.
Yes, sir. Sir, definitely those I will forward this, sir.
Yeah.
I'll share your email ID after this session, sir.
Yeah, sure.
Sir, thank you, sir. Thank you for the wonderful.
Okay. Yeah, I have a request. Okay. Now, some details of this program, because I just came back from US, so I'm not completely aware of the. Can you send me kind of brochure or a program book for your?
Sir, I have mailed to you, sir, already.
You have mailed to me?
So once again, I'll send it. Once again, I'll send it, sir.
What I wanted is the different lectures that are being planned, and then the others, so that if necessary, I might want to get in touch with them.
Sir, sure, sir, sure, sir.
So that is the, see,
Yes, sir. Yes,
I
sir.
saw this Satish, right, who was talking earlier.
Yes, sir,
Okay,
yes, sir.
I could spend some
Yes, sir.
time understand what he's talking. So some of those things can be implemented here. So I would like to get in touch with those kind of people who we can exploit their expertise.
Sure, sir, sure, sir. I'll
Yeah,
send you.
so send me that information.
Sir.
Okay,
Sure, sir, sure. Okay, sir.
thank you very much.
Thank you, sir. Thank you.
Yeah, right.
Participants, kindly mark your attendance using the feedback link. So now
Okay.
Karthik sir will share it in you. Thank you.
Okay, so I'll be signing off.
Yes, sir. Thank you, sir. Thank you so much.
Okay, right.
Okay. Just you can press stop sharing, sir. Then you can use.
Okay, that's what I'm trying to do that.
That's sir.
Okay, done. Right.
Sir, right. Okay. So thank you everyone. So again, we'll meet you in the next session. So kindly everyone fill that Google form. So for both the sessions, session 5 and session 6. So meet you tomorrow. So thank you. Thank you.